Hi guys, we're doing 1977 M2. So the situation here is we have a cylindrical mass that's being pulled up by a string. Due to this pulling, the mass will accelerate in one direction or the other. Now we'll go to Tim for the free body diagram.
Where's my marker?
Okay, so you gotta start by drawing the system. And this system is on a horizontal surface. So there's a force gravity and there's also a normal force. But there's also a force tension that's pulling up at the same time. So force tension T, force normal, and force gravity. And there's also a frictional force opposing the direction of motion. So we'll just arbitrarily put it here because the force can either be positive or negative based on the summation equations. So it doesn't really matter where we place the force of friction. And so that the rotational and translational acceleration match up, we'll put the sign convention as shown. So it's it should be accelerating in the left direction, and it's also accelerating rotationally counterclockwise, so that the sign convention is out of the paper.
Now we'll go back to Eric with the calculations. Alright, so now we're gonna try and calculate the angular acceleration of the cylinder. Oh wait, no, the linear acceleration of the cylinder. Alright, so we're gonna first write out our summation equations like good students. So here's our torque summation equation, right? Now, we're gonna have to put the fulcrum in the middle because that is where the center of mass is, and we want the fulcrum to be in the same place as the center of mass so that the angular acceleration and the rotational acceleration are relatable. Okay, so first we start with our torque equation. So we're gonna have T and then R. That's our first torque here, plus force of kinetic friction times R. Alright, now we're gonna move on to our force equation. So we have in the y direction force gravity, which is negative, plus force normal, plus tension force. That means that the tension force is equal to the force normal is equal to force gravity minus the tension force. And we know both of these values because we have the mass of the cylinder, so we can just say that this is mg. And they tell us that the tension force is 0.6. Is it 0.6?
Yeah, it's 0.6.
0.6 mg. Alrighty. So now we have force normal. Now we're going in the x direction. There's only one force in the x direction, and that is force of kinetic friction. Okay? So mass times acceleration is equal to force of kinetic friction. Now, we're going to say that mass times acceleration must be equal to negative mu Fn, because that is what force of kinetic friction is. Now, we can set that equal to negative mu times 0.4 mg, as we stated here before. Now we know what mu is. It is 0.5. So we can solve this real quick and say that it's negative 0.2 mg. Alrighty.
Acceleration.
That is acceleration.
No, that's force.
Shit.
No. No, whatever, dude. Okay. So it goes 0.2 g.
Alrighty. Now we'll go to Tim for the angular acceleration.
Oh, wait, where's the torque? Okay, so I have to rewrite the torque equation. It's the same thing. It's torque equals I alpha equals force, kinetic friction R plus force tension R. And these are both positive because of our sign convention. And so the moment of inertia of the cylinder is 1/2 mr squared. And we're just going to put alpha because we can't apply the rolling constraint to this rolling with slipping situation. And we just calculated the force of kinetic friction, or the acceleration. So we just multiply 1/2 g by the mass, and you get the force of kinetic friction times r, plus force of tension, which is given as 0.6 mg times r. And we can sum these values together to get 1/2 mr squared alpha equals 0.8 mgr. And then when you solve for alpha, you get 1.6 g over r. And Eric will cover part D.
Alright, so part D asks, why is it that acceleration does not equal alpha r? Why is this? This is a great question. So, we calculated acceleration to be 0.2 gr. Oh no, 0.2 g, I'm sorry.
It's not okay.
Alright, and alpha equals 1.6 g over r. Clearly these are not equal. And this is because we are rolling without slipping. Alright, fine. Multiply by r. I guess you can't see it yourself, so I'll do it.
Thanks, Eric.
It's equal to 1.6 g. 1.6 g does not equal 0.2 g. So, the reason this happens is because the object is slipping while it is rolling. And that means that the rolling constraint does not apply. Because energy is lost due to friction, and the cylinder slips on the surface. Therefore, A cannot equal alpha r.
Thanks for joining us for a day in physics. See you next time.